we are given a gradient function, f prime of x, and we are told that there's a certain point, c comma 0 is on this graph. We are looking to sketch the original function, right? So we need to anti-differentiate, and we are also given that that same point is on the original function. Cool, and the scales are the same, right? So that's helpful. So first of all, looking at our gradient function, what type of graph is it? It is a quadratic, right, or a parabola. Is it a positive or a negative quadratic? Right, it is a negative quadratic. So that means when we anti-differentiate it, what do we expect to get? So, for example, negative x squared, if we took the antiderivative of that, we would get negative x cubed over 3. In other words, the antiderivative of a negative quadratic is a negative cubic. And a negative cubic looks something like that. So it decreases, increases, decreases. Its minimum is before the maximum. So with that, we know that this graph is going to look something like that, except it has to go through that point. But exactly how it looks, we need to now consider a few key points. Okay, so on our gradient function, two very important points are the x-intercepts, because that tells us that the gradient f prime of x is 0 at those x values. So since these grids line up, I will drop a dashed line down. So at C, it's here, and at this intercept, it's here. So just putting those through. And these dashed lines will help us construct the original graph. All right, and I did them dashed just so it's clear that they are not part of the graph. So what that means is, since the gradient function, the y value is 0 at those two x values, the original function will have its turning points in line with those dashed lines. And we know it's a minimum and then a maximum, right? Because we know a negative cubic has the minimum first. All right, so we also know that point C is on this graph, and that is on the dashed line. So actually we know that there is a minimum there. So we could start our sketch like so. We also know that there's a maximum on the right dash line. So just connecting them, so minimum, maximum, oh, take two, minimum, and then maximum. A little bit better, but still a bit wonk, but you get the idea. As long as the minimum is at point C and the maximum is in line with that second dashed line, because that is in line with the x-intercept of the gradient function. Cool. And that is actually a merit question, right? If we got those turning points exactly in the right position and it's a negative cubic, merit. If you didn't get the turning points quite right, you can still get achieved for this question. But let's have a consideration about the other gradients, namely between the turning points, the gradient has a positive value, right? F prime of x is positive, so between our turning points, this gradient should be positive, which it is. And then outside the turning points, so to the left of C and to the right of this value, the gradient of our original function should be negative, right? Which it is. So that lines up with our expectation of it being a negative cubic. And it kind of looks like a beach chair. Okay, I don't know what I just drew there, ignore that, and have a nice day.